University of Cambridge in chemoinformatics, particularly in computational toxicology. And this presentation is going to be about some of the research we conducted on understanding significant polypharmacology in chemical-induced toxicity using the ToxCast and the Tox21 data. So the new approach, or the new toxicology approach, commonly referred as IATA, is mainly intended to reduce, refine, and replace animal use for its toxicity evaluation. And these approaches are used to prioritize testing and identify and characterize hazard, as well as to assess risk according to exposure. And we can roughly categorize the IATA into three categories, mainly mode of action analysis or adverse outcome pathway analysis, in vitro in vivo extrapolation, and also using the data to store the data that have been accumulated within decades, and also to perform data mining. So the use of IATA in general involve the use of two or more approaches, including physiochemical properties, in vitro assays, mode of action analysis, kinetic models, and in silico models. And it is aiming to provide a mechanistic-oriented system for an efficient safety evaluation. And that's through improving our understanding of the mechanism of toxicity to rationalize the decision-making, the toxicity assessment, and also to prioritize the in vitro models for the relevant toxicity outcome. And what we observed in the years is a variable acceptance by the regulatory bodies, usually slow, especially due to the problem of the black box QSAR models, where it might not necessarily provide a mechanistic understanding on why we observe the toxic effects. So in this presentation, we would focus on the use of data, but not to perform a prediction, but to understand the mechanism of toxicity, and in particular the polypharmacology of toxic compounds. So the use of QSAR model in general have been proposed to predict properties such as toxicity, bioavailability, and ADME using chemical descriptors in the aim of getting as close evaluations as the experimental values. And as we mentioned, the problem with that is that it might not provide a mechanistic understanding if the outcome is just a numerical value or a binary category of a yes or no, toxic or non-toxic. And there have been a plethora of building models in order not only to predict the toxicity, but also to extract patterns from chemical features, multi-omics data, imaging, and bioactivity, as well as in vivo outcomes and clinical effects. And that have been demonstrated by the plethora of studies that have been published in the literature to predict various types of toxicity, such as hepatotoxicity, cardiotoxicity, and other types of in vivo outcomes. But to really understand how toxicity is triggered at the molecular level, we need to better understand the biological perturbation within the cells. And a good example or a good framework to describe this is the adverse outcome pathway, which is a series of events starting from perturbation at the molecular level and represented as molecular initiating event, and which progresses in a cascade of events that escalates from cellular to tissue and ultimately at the in vivo or individual and even the population level. In order to use the data so that we can understand how perturbation at the molecular and cellular level would lead to adverse outcomes at the individual level or in the in vivo and clinical level, what we can do is that we can mine statistical associations from the data that we have gathered so far from the changes in molecular and cellular level against the observation of toxicity animal and human, and then we can generate hypotheses about these mechanisms of toxicity. And in order to do so, we have two important components. One is the interpretable features, and the other is the interpretable algorithm. With regards to the interpretable features, is to describe the compounds either in form of substructures or toxicophores, physicochemical properties, or with regards to the biological effects at the cellular or molecular level, which can be then used to mine the associations. And the algorithm has to be also interpretable, so either direct bivariate associations or similarity among the space, or using some algorithm that take into consideration multivariate effects such as multivariate models, such as regression and decision trees. In a previous study, we've integrated data from ToxCast against reports from clinical effects, where we derived hypotheses about structural carriage toxicity. And here this illustrated a proposed adverse outcome pathway for structural carriage toxicity, in particular the valve incompetence, where we used bivariate associations, where we combined measurements from in vitro activity in ToxCast against clinical effects reported in the FDA Adverse Event Reporting System, the FEARS data. So it shows that we can use data to mine or to generate hypotheses about mechanism of toxicity. However, the problem resides that compounds rarely have one single biological action and are rather characterized by polypharmacology profiles. So toxicity might not be triggered by a single molecular initiating event, and we need to explore how the combination of molecular initiating events or combination of bioactivity profiles, in addition to chemical properties, would lead to toxicity, rather than just looking at the problem in a bivariate case. And to demonstrate this, the AOP network has been proposed to analyze these interactions, which consider multiple key events and molecular initiating events. However, the state of knowledge of the current AOP network is still limited and incomplete, which might limit the utility of this network in the current time to be used for toxicity assessment. So in order to overcome this issue, we should look at it from a database problem, where we consider that if we consider that toxicity represents a combination of assay and chemical feature, how we can use this assumption to build a model that we can use to generate hypotheses about the polypharmacology or the conditional associations between the chemical properties and the toxicity. One way to achieve that, and this is the algorithm that we have been using it in our research, is rule models. And rules are basically a set of feature conditions which are associated with another variable and presented as an if-then statement. So in this hypothetical data that is labeled from A to H, representing the input variables or the bioactivity measurement or the chemical features against the toxicity label L, where the red is the presence of toxicity and L is the absence of toxicity. We see that feature E, when it's present, it's likely that the compound is going to be toxic. However, and that effect is not as strong in G and C. However, if we look at the intersection or the combination of the feature C and feature E, we find that there is high likelihood to observe toxicity. In other words, if feature E is present and feature C is present, then L is present, or the rule is described if E is green and C is green, then L is red, which means that there is high likelihood in comparison to comparing and to describing the compound as the one feature, for example, E. And one of the key search algorithms that have been used to search for these combinations is called entropy, which builds up um, the feature combination iteratively, and it's very common to construct trees and rule models. The problem, however, with the conventional rule or tree model that they do not respect direction of association, which is important, and it's the way where we interpret how toxicity can be triggered. So, for example, we would say if the compound is active against this assay, then we would likely see toxicity in vivo, and this is also manifested in how the adverse outcome pathway are structures where they represent key events linked by directional relationships in the key event relationships. And to illustrate this more, if the rule would, for example, capture the association between observing the mitochondrial impairment in vitro with toxicity in vivo, then that's a biological meaningful association. However, if the algorithm would detect the absence of cytotoxicity to be an indicative or predictive of toxicity, this is biologically irrelevant. So it is very important to control over these associations. And the way to do so is by applying constraints on the algorithm or in the search algorithm so that we would only generate or extract biologically meaningful associations. And that would improve eventually the interpretability of the patterns that we observe in data. The way we did so, we proposed two workflows or two ways to apply constraints on rules. One is based on continuous data where we apply rule modification, and the other is based on using categorical data or binary data by using constrained emerging patterns, and we will explore this a bit further. So the first approach, where we build models to describe toxicity using a combination of bioactivity measurement and chemical properties, for example, the chemical properties in continuous variables, and then after generating the rule, conditions that describe inactivity in assay is removed. So we apply rule pruning. Then we re-evaluate the modified rule, and those that satisfy the minimum requirement pass and are used to explore the patterns and to guide into understanding the mechanisms of possible polypharmacology or mechanism of action. The second approach is based on emerging patterns where the data is converted into lists of features, and then emerging patterns, which is a type of rules which finds frequent item sets of features that are discriminating between the two data labels. So, for example, which are the lists of features that are present in one type of data but not the other. And this method have been applied to extract or to explore substructural RRs and toxicophores. So we would explore the use of these rules with constraint to prioritize in vitro assays for hepatotoxicity, and well as to understand polypharmacology and acute toxicity. For the first example, we used rule modification for prioritizing hepatotoxicity assays. Hepatotoxicity in general is a complex adverse event where it involves multiple pathological pathways, which can be really difficult to capture. And the problem with in vitro models for hepatotoxicity is that they might have high specificity but low sensitivity, which means that if the assay would not be able to detect an activity of the compound, it doesn't mean that the compound is safe. So the question becomes is what are the bioactivities that can be really predictive of hepatotoxicity? What are the combination of bioactivity features or biological perturbations that if we captured, we would have a better coverage of toxic compounds? And the second question is, what are the chemical properties that might affect the concordance or the transferability of in vitro measurements and the in vivo observations? So in this study, we've used data from the ToxCast using the AC50 data, along with 29 calculated physicochemical properties, including electrophilicity, molecular weight, and number of rings, against relative observations from the ToxRef database, where we discretized the LEL into two categories: compounds that are toxic at the level of 15 milligram per kilogram per day, and compounds that are toxic at 500 milligram per kilogram per day. And the reason we did that, we wanted to compare whether we would see variable biological space of the compounds that are potent, that are toxic at a potent level, with those that are less potent, or whether we would see a variability in the chemical features. So we constructed rules where the rules were describing hepatotoxicity using bioactivity from the ToxCast data as well as physicochemical properties. And we applied, in this case, the pruning method, where rules that where inactivity in inactivity conditions or activity in assays used by the rules have been removed. Then we reassess the rules, and the rules that pass the test are used to identify the biological space of important key events or important endpoints for in vitro models for hepatotoxicity, and also to explore the bioactivity physicochemical interactions. Looking at the generated rule from the algorithm, we observed that in average, the rule contained one active condition, so which means that only an average one activity in assay have been used by rule, whereas 4 inactivity have been used in a rule, and one physicochemical property condition. So the rule would consist of, for example, in average, it would include 1 positive activity and 4 negative bioactivities. And we also observed that the abundance of physicochemical conditions are lower at the low potent level. This is an example of how we conducted the pruning. So in the left side, we see the original rule. So it would be construction of a combination of assays describing activity and inactivity. And the way we defined activity and inactivity by assay is how the split is formed. So activity would be represented as a split that is below a concentration threshold. So it would be, for example, an activity at a threshold of, for example, 1 micromolar. So what is less than 1 micromolar, if the rule uses less than 1 micromolar in this assay, it means that it's indicating the activity. But if it's describing an assay where it's higher than 100 micromolar, then this is a condition where it's described an inactivity. So wherever we find that the assay is described as the inactive form, we remove that, and then we reassess the modified rules prior the analysis. So the overall workflow would be first generating the rules, applying the rule modification, then reassessing the performance of the rule, where we at this stage we do rule prioritization with regards to accuracy and with regards to coverage. So rules that satisfy at least 70% accuracy and 50 compounds coverage for the 500 milligram per kilogram per day rules and 20 compounds for the 50 milligram per kilogram per day rules are kept. Then we do another level of selection where we only select rules that in combination they would cover 80% of the toxic compounds in the dataset. So, and the way we did so is by ranking the rules according to the accuracy and then plotting the accumulative compound coverage by these rules. And whenever we reach 80% coverage, we use these rule subset, which we would then hypothesize that these captured the important endpoints that have the maximum coverage. And another step that we performed is applying clustering on the rules to identify the clusters of rules that would represent different types of compounds. So we would look at what type of cluster of bioactivity clusters that have been presented in the rules. So what we have observed, so in these tables, it lists the endpoint, the ToxCast assays that have been used in the rules and the clusters, and we observe similarity in the bioactivity clusters between the two toxicity thresholds, where both of them have three main clusters represented by cytochrome P activity, immunological response, and nuclear receptor activity. And wherever the L sign, it demonstrates where a rule has used more than one assay at a time. So it's a multiple bioactivity or a combination of bioactivity in a single rule. So the rules, although they mainly showed single positive bioactivities, but in some cases multiple assays have been used. Another thing that we've also explored is how the endpoints that have been captured in the rules compare with commercial setups for hepatotoxicity. And in this case, we have observed across different type of endpoints, including cytotoxicity, cell loss, cytochrome activity, cell stress, and mitochondrial impairment in general. So the endpoints captured in the rule represented a combination of what have been screened for in commercial setups, except for endocrine activity, which is a key cluster according to the data, to our data. So which involves a diverse biological space, including the endocrine activity, which represented an independent cluster. What does that mean? If we want to improve the coverage of hepatotoxic compounds by in vitro models, we need to also incorporate nuclear receptor activity or estrogen endocrine activity. To briefly just also cover on the combined bioactivity readouts and why we are observing these. So for example, at both thresholds, we observe the combination of the androgen receptor activity and the PPAR, the peroxychrome proliferator activating receptor. And it has been known that there is a bidirectional crosstalk between these two nuclear receptors, where each one influence the expression and the function and the transcriptional activity of the other, which was really interesting to observe. Which means if we have if the compound if the compounds show activity against these two nuclear receptor, it's likely to be hepatotoxic. Another observation is the combination of cytochrome P, C2 enzyme, and activity of the vitamin D receptor. And it's also interesting because vitamin D receptor regulates the expression of cytochrome P. So, and what the data says is, the data shows if the compounds have shown activity against the cytochrome as well as disrupting the vitamin D receptor activity, then there is a higher likelihood of observing hepatotoxicity. And a third example is the combination of estrogen receptor agonist and the chemokine ligand 9, where it has been shown that there is a link in the expression. So the estrogen treated might have shown significant reduction in the expression of this chemokine, and where it's associated with liver fibrosis. And what the data suggests is that if the compound is an estrogen receptor agonist and it's also disrupt the expression of this chemokine, then the likelihood of observing hepatotoxicity in vivo is higher. In addition to these assay combinations, we've also explored how physiochemical properties affect the in vitro, in vivo associations. And the plot here shows the change in error rate or change in accuracy in rules by removing physiochemical property conditions. And we observe a variable change in accuracy and a variable change in error rate by removing physiochemical properties according to the assay class, and which is most notably with nuclear receptor assays. So what does that mean is if the rule describes a disruption against a nuclear receptor and that rule uses a physiochemical property, then this rule is very dependent on this physiochemical property, given that the assay describes a nuclear receptor disruption. So for example, if we compare that with a cytochrome P, especially at the low potency, there is less need of a physiochemical property. So the use of these physiochemical conditions is dependent on the assay class. And the most frequent property that we've observed is number of rotatable bonds at the 15 milligram per kilogram per day level, and the number of rings at the 500 milligram per kilogram per day level. What was interesting is that the cutoff by which these conditions have appeared in rules were in alignment with what have been reported in literature to describe good bioavailability. So, for example, the most frequent physiochemical conditions in rules describing toxicity at 15 milligram per kilogram per day is the number of rotatable bonds to be less or equal 6. And it has been reported that having 10 or fewer rotatable bonds is likely associated with good bioavailability and good permeability, which indicates that biological disruption or activity assay is not enough, and if we combine that with the relevant physiochemical property, then we would have a better transferability into in vivo outcome. And also with regards to number of rings, the hypothesis, what we observed from analyzing the literature is that number of rings is associated with plasma protein binding, which means that if we have larger number of rings, there is higher plasma protein binding, and then which consequently lead to smaller concentration or a fewer concentration of the free free form of the compound in the plasma, which indicates a lower bioavailability of the free form. Another observation is that the toxic compounds have shown higher promiscuity over the rules. In other words, toxic compounds significantly match more rules than the non-toxic compounds, which means that when we match more hepatotoxic liabilities in terms of assays and the relevant biophysicochemical properties, the chances of the compounds to be hepatotoxic is greater. Something that have been demonstrated so much in the literature is how well in vivo outcomes can extrapolate into humans. So the data that we have used here is hepatotoxicity in rats, and it has demonstrated that that the outcomes of animal studies do not extrapolate well into human. So one of the observation in our findings regarding to the compounds or the drug droglitazone, which is an antidiabetic that have been withdrawn due to hepatotoxicity. These compounds is labeled in our data as toxic at the 500. There is a typo here. It's labeled as toxic as at the 500 milligram per kilogram per day, but not at the 50 milligram per kilogram per day. However, the promiscuity of this compound against the rule was greater than 75% of toxic compounds at the 500 milligram per kilogram per day level, and equivalent to the average toxic compounds at the 50 milligram per kilogram per day level, which means that although the hepatotoxicity or the animal outcomes might not necessarily extrapolate directly into human, but it can still be used to infer associations which are relevant to the biology and the biological perturbation that can describe effects in human. For the second example, where we used emerging patterns to understand polypharmacology in acute toxicity, several target-based and mechanisms for acute toxicity have been proposed, including GABA receptor inhibition, mitochondria impairment, the dopamine receptor antagonism, and most common mechanism is the acetylcholine inhibition. However, we would acknowledge that acute toxicity might not arise or be triggered from a single molecular initiating event, and it is rather a very complex event. So in order to capture the multi-conditional associations between molecular initiating events and key events that can trigger acute toxicity in vivo, we need to use methods that would respect the multi-conditional associations, and where we can derive hypotheses between the polypharmacology and the adverse outcome in vivo. And for this, we've used data for the acute toxicity using the GHS system, the globally harmonized system for acute toxicity, where we considered the GHS class 1, 2, and 3 to be for this study to be toxic, whereas we hypothesized that the classes 4 and 5 are non-toxic. For the bioactivity data, we used the Tox21 bioactivity measurements in percentage, as well as an in-house tool for target prediction, where it predicts and annotates binary target activity across over 1,000 targets. And for the Tox21 activity, we discretize the endpoints, the percentage endpoint into different bins, where the activity were given 4 categories: either greater than 20%, greater than 40%, 60%, and 80%. And because we can't generalize the bioactivity cutoff that is more relevant to toxicity, so we've used multiple levels of activity cutoffs. In addition to the bioactivity data, we use substructures to reflect toxicophores using tox alerts data from the OCHEM server, as well as substructures that are frequent in the compounds in the dataset using the MOSS node in 9. And the integration of the data resulted into around 2,000 unique compounds of completed or complete measurements, which have been used to generate the rules. And in this case, the emerging pattern or the rule method that we've used is the C bar, which represents classifications based on predictive association rules. And basically what it does, it takes a data in a list or a transaction form, which means just a list of features to describe the toxicity or absence of toxicity in a combination of these features. And the overall workflow, we took the data, generated the rules, and in this case, the constraints that we applied where we generated toxic rules to be described by the presence of bioactivity, presence of this substructure, whereas the absence of toxicity or non-toxic rules are represented by the absence of the bioactivity and a presence of the substructure. And these rules have been analyzed in 2 key ways, mainly by looking at the synergy between condition pairs and also looking at the rule at the networks, where we analyze the cluster of rules and we analyze the adjacency of features in the rules. In this analysis, we've generated thousands of rules that have an average accuracy above 80%. What we also observe is that the rules that are only represented by a single condition is less than 10%, which means most of the rules that have been generated contain 2 or more conditions or 2 or more features. With regards to the single condition rules, the most frequent ones represented were describing potent cytotoxicity or substructure alerts, and this can be explained by the strength of association between the individual features and the acute toxicity. We've seen that cell viability or cytotoxicity as well as substructural features has the strongest univariate associations in terms of mutual information in comparison to the other classes of features used, and that explains why those most were dominating single condition rules. But in order to explore the polypharmacology by the multi-condition rules, we used synergy score that analyzes how synergistic a pair in a rule comparison to individual features. And in order to do so, we use the synergy metric from the mutual information, where the synergy is calculated by the difference in the mutual information between the mutual information of the rule and the sum of mutual information for the individual features. And the other method is dependent on the odd ratio, where the odd ratio of the rule is compared with the product of odd ratios for each individual features. And in both cases where the mutual information of the rule is greater than the sum of mutual information of individual features, or the odd ratio of the condition pair is greater than the product of odd ratios, the pair is considered to be synergistic, which means that the likelihood of observing toxicity is beyond the additive effect. In this case, synergistic pairs have shown to be dissimilar, and this dissimilarity was with regards to their chemical profiles and biological function. And this makes sense, which because if the both features are redundant in the information or describe a similar biological function, then it's less likely for them to be synergistic. So, however, not all dissimilar feature combinations were synergistic, but the majority of synergistic pairs were dissimilar. And here are some of the interesting examples and the frequent synergistic examples that we found in our rules from the available data. Interestingly, we saw a dominance of nuclear receptor activity, although nuclear receptor disruptions such as androgen activity or estrogen activity on their own would not describe how compounds will show acute toxicity. They are more associated with chronic effects. However, what we observed, if the compound is active against androgen receptor or estrogen receptor and bear as a heterocyclic ring, there is a strong association with acute toxicity and a very high likelihood for the compound to be to exert acute toxicity. And when we tried to interpret that from the literature, we found that heterocyclic steroids have been reported to have an enhanced activity and can produce neurotoxicity and convulsions, which may explain in this case how some of these nuclear receptors might not, on their own, might not be exploratory of the acute toxicity, but if we looked at the conditional associations, we might understand better why we observe these effects. Another interesting example is the glutamate receptor and the GABA receptor. These are two commonly known key events in acute toxicity, and these two have been both commonly associated synergistically linked with thyroid hormone receptor antagonism, and the combination of the compound to disrupt glutamate receptor or GABA receptor and to be antagonizing the thyroid hormone receptor have shown a strong link and a strong likelihood to be acute, to have acute toxicity. And that can be explained that thyroid hormone receptor are regulating the neuronal uptake, the expression and the function of both GABA and glutamate receptor. And that means that when the compounds bear both glutamate receptor disruption and thyroid hormone antagonism, or GABA disruption and thyroid hormone receptor antagonism, there is high likelihood of the compound to be acutely toxic. Another interesting example, and it's reoccurring from our previous study, is the combination of the cytochrome P and the VDR. What we observe here is that the cytochrome P have frequently associated with the nuclear receptor that regulate the expression of cytochrome P enzymes in general, such as the VDR, the AHR, and the CAR. And it was interesting to see, which means that when analyzing the data, the cytochrome activity data for the potential of toxicity, we also should be looking at whether these compounds also mutually activate or deactivate the relevant nuclear receptor. And another example is the acetylcholinesterase. So acetylcholinesterase is also a known key non-originating event in acute toxicity, but it has shown numerous synergistic links in the rule. What I would like to focus on is the troponin and the NLRP3. The troponin it regulates the cardiac contractions through calcium ion sensitization, and it has been reported that in a cholinergic toxidrome, and calcium ion dysregulation occurred, and as well as in inflammation with regards to the with the NLRP3 inflammasome. Um, this inflammasome regulates a highly potent inflammatory cell death pathway through activating the caspase 1. And what the data shows is that there is a frequent link and a synergistic link between this inflammasome and the acetylcholine esterase inhibition. Um, the second part of the analysis of the rules, we also looked at the macro patterns within the rules using the network analysis, where we captured rules in network. We looked at the adjacency of the features in the rules, where it is represented in a network where the nodes are the features and the edges reflect whether knot pairs co-occurred in one rule. And in this case, the features were colored according to the feature type. We applied clustering on the network. We've observed a mechanism-based clustering where cytotoxicity and cell viability in the light blue have been separated from target-specific mechanisms, such as the enzyme and kinases in pink and red, which means that we cannot replace target-specific endpoints to replace the cytotoxicity assay. We have to use them in combination because some of the compounds might not be captured by target-specific endpoints, but can be captured by cytotoxicity. In the network, we've also observed some of the commonly known mechanisms of acute toxicity to be very central in the network, in addition to the abundance of nuclear receptor disruption, which, as we mentioned, cannot be explained on their own on how they trigger acute toxicity, and we need to look at the polypharmacology. Another interesting observation that we've seen is how the connectivity of Tox21 assays at different potency level are located in the network, or they perform in the network. What we observe is that assays that are describing low potency have higher connectivity. The degree connectivity just reflects number of unique edges, and if we recall, the edges represent co-occurrence of the knot pair in the rules, which means that conditions of low potency in Tox21 assay required many other companion features in comparison to potency in the Tox21 assays, such as in the case of, for example, at 80% level, where there is low connectivity, which means low mutual other conditions in a rule. So they extrapolate on their own well into toxicity compared to assay conditions that reflect low potency. And what we can learn from here is that exploring polypharmacology is especially important at low potency, while we can extrapolate well high potencies in assays into in vivo outcomes. There is no direct or no way of how we can capture the effects of the polypharmacology at low potency, which what we observe here is it should not be neglected. It's the acute toxicity can still be triggered by multiple by activities of low potencies. And a final representation of what we can do with these rule networks, we can visualize a compound-specific rule network where we can visualize and navigate polypharmacology in compounds. So in the left side, it's a representation of the rule networks of toxic compounds, where we see an overactivation of cytotoxicity cluster, the light blue knots, in comparison to the right side of some of the non-toxic compounds, where it shows an overall weak activation of the nodes or the weak of the network clusters. However, some of the non-toxic compounds are promiscuous, where they are characterized by activating lots of edges. When we compare it with toxic compounds that are also promiscuous, what we find distinguishing between the two is the density of synergistic links. We saw that when the compounds show a synergy density higher than 15%, which are represented by the blue lines, the blue edges, there is 3.5 high odds of the compound to trigger acute toxicity, which means that the promiscuity as such might not be is not a good predictive of toxicity, but we need to look at what are the constituents of these combinations, what are these combinations mean, and whether they are significant, whether the polypharmacology is significant or not. And then I will just conclude this presentation by a few statements. So hepatotoxicity cannot be well captured by single assay points, but we need to look at a diverse bioactivity space in relevant assays, where we observe that the likelihood of toxicity of hepatotoxicity increases with assay promiscuity. And we've also seen how incorporating physicochemical properties improve the in vitro in vivo associations, such as the use of a number of rotatable bonds, which reflects good bioavailability, and this is especially important for describing toxicity at a potent level. And with regard to acute toxicity, in order to properly capture acute toxicity using in vitro methods, polypharmacology should be considered, especially at weak potencies, which are usually overlooked using conventional extrapolation methods. And we've also observed specifically synergistic polypharmacology between some of the known key events of acute toxicity and their relevant and the destruction of their relevant nuclear receptor or regulating nuclear receptors. So we can conclude from this work is that understanding the significant pharmacology can be used to better leverage the in vitro models and can guide cost and time effective iterative screening protocols for toxicity assessment. And yeah, I would like to thank my colleagues at University of Cambridge, including my supervisor Andreas Bender and Dr. Franz at the University of Liverpool for helping with the algorithm, the emerging pattern algorithm, and Dr. Igor for helping with the OCHEM server, and also Lilia and Jonathan for their valuable discussions, and also Russell for enabling this presentation. Yeah, and thank you very much for your attention. I'm happy to have any questions.
Yeah, thank you. Looks like we got some questions in the chat right now. Let's see. Can you see those right now, or do you want me to read them out for you, Dr. Mahmoud?
Let me get this through. Yep.
Do we lose you?
Yeah, I'm there. I'm just trying to find. So the question out in the chat.
Yes, and so I think the first one was from Andrew, right there. Can you see that?
1 second, let me check. I'm not sure if the chat box that I have is updated. Andrew.
If we're having a problem with that, then I can just read them out for you if you can't see them. Does that work?
That would work, yeah.
Okay, cool. So let's see. So the one from Andrew is, to avoid overfitting, did you try cross-validating or separating based on training/test sets?
Yeah, so for example, with regards to the hepatotoxicity model, in the first instance, the rules were generated from cross-validation. So what we did is that we had a five-fold cross-validation model to generate the original rules, and then we took the rules that have from the models that performed the best in each. So we've run that 100 times in 100 iterations, and in each iteration, the default that performed the best, we selected that to generate the rules. And something that I haven't put here just because of the time restriction is how we validated our rules. So we used some of the drugs with drug-induced liver injury labels from the FDA website, and also they would have like ToxCast measurements recorded, but they were not used in the training. And what we observed is that the drugs were the most deadly concerned had higher promiscuity over the biological space captured by the rules. So we did, yeah.
Okay. And then, go on, sorry. I didn't mean to cut you off.
Yeah, so we did a validation on that. With regards to the acute toxicity, it was mostly exploration. So we explored the polypharmacology, and we tried to evaluate the observations that we've seen. I've not included all the patterns that we've observed, so I've just picked some of the most frequent ones and the most interesting ones. But we were able to explain around 80% of the patterns and the synergy links that we observed. Yeah.
Okay, cool. Yeah. And then the next question is from Judy, and they want to know, has the work on acute toxicity
right, so that
been
hasn't
published?
been published yet. The hepatotoxicity work is about to get out from the Chemical Research and Toxicology, so that is due to be out. But the work on acute toxicity is not published yet. But if you'd like, you can just contact me in my email, and we can discuss this further if you'd like.
Okay, cool. And so let's see. Next up, we got a question from Sergio, and they want to know, where can a model to get the rotatable bonds be found?
So I'm not sure if I got you there, but what we did is that we used physicochemical properties in a continuous form, and the rules detected that split. So we didn't enforce the what physicochemical property to be used, or what splits, what is the best split. For example, what the rules found is that number of rotatable bonds are equal or less than 6 or less than 7, but we haven't enforced that. So the algorithm, the rule, would search among the input variables and would select the best condition. And what we found is that the number of rotatable bonds, one of the most frequent condition, irrespective to the assay type, that has been used by the rules. And the way we calculated these physiochemical properties is through the RD kit package. I'm not sure if that answers your question, but just let me know if that needs further clarification.
Okay, cool. And we've got another question from Andrew, and it is, so from the mechanisms you've discovered, is it possible to tell which types of experiments are needed along each point of the AOP?
Right. So for example, if you have lists of AOPs, so for example, from the network perspective, if you're interested in a specific key event, you can look at or you can trace what were the adjacent nodes, which represent the direct important conditions. And from the data, we can also label the importance of these edges. So the edges that represent synergistic links or important combinations have higher synergy scores. So if that molecular initiating event, for example, glutamate receptor, so the compound is active against glutamate receptor, we would look at the other important key events that in combination the likelihood of toxicity increases. So the starting point would be the known key events, and then to explore whether we are going to see the acute toxicity or other type of toxicity. So this can be generalized to any type of toxicity, but we can look at the other important molecular initiating events or other key events that should be also analyzed in a company of the key of the classic or the known key event.
Okay, cool. It looks like Andrew is typing again, but see if he has a follow-up, but otherwise, I think we're going to wrap up. Okay, so and now Andrew wants to know, so there are so many readouts, do you think fitting the data to a causal structural equation model will be simpler when mapped to AOP?
So what we haven't considered, for example, with the acute toxicity compared to the hepatic toxicity, is the minimal amount of patterns that are required for maximum coverage. So because the idea was to explore the polypharmacology that we are not aware of. So it's less than the idea of what are the key predictive key endpoints, but it's how to go beyond what we already know, how to go beyond the single molecular initiating event and beyond the state of knowledge of current AOP network. So there might be multiple methods that can be simpler, but because of the high dimensionality of the data to start with, we need to use algorithms that can handle high dimensional data. So that's why we use the rules. And so, for example, the input variables in our case is in terms of thousands, so over 3,000 input variable, which have been reduced to around 500 nodes, around 500 nodes in the network, which represented the nodes that or the features that have been used by the model. Then we looked at those that have the key patterns, the highest connectivity, the highest univariate association, the frequent synergies. So it's more of like exploratory of the polypharmacology. I hope that answers your question.
Yeah. Yeah, I think Andrew said thank you in the chat, so I think that he is all good. I think with that, we might just take the opportunity to wrap it up. If no one has any more questions, I don't see anyone typing. But thank you so much, Dr. Mahmoud, and I just want to invite everyone to please join us next month. We'll be hearing from Dr. Maureen Gwynn at the EPA, and she will be presenting on the Accelerating the Pace of Chemical Risk Assessment project. So thanks so much for joining, everybody.
Thank you. Thank you so much. Thank you, everyone.
Goodbye.